Mm, And I am live. That is cool. Internet is also now fine. Okay. So today is 13th of September 2025, Saturday, and I started streaming late. So let's just skip the foreplay and get down to dynamic programming. Yep, video is stopped here, and that is pretty nice. Elements of dynamic programming. Yesterday we did this thing. We also did all of the exercises, which makes me feel happy because I don't do exercises usually. So yesterday we did this one, matrix chain multiplication, in which we had to find a sequence in which we can multiply matrices together. And if we multiply matrices in that particular sequence, since matrix multiplication is associative, if we multiply matrices in this particular sequence, we would have to perform the least amount of scalar multiplications, and that is pretty nice. And before that, there was the rod cutting problem, which was also nice, pretty nice. And we also know about the four things we do when we want to do a question when we want to find answer to a question using dynamic programming. And those four things are: characterize the structure of an optimal solution, write down what an optimal solution would look like, and recursively define the value of an optimal solution. That is, if you know the optimal solution for some smaller subproblems are smaller for some subproblem, then how would you use that solution to subproblems to find the optimal solution to your bigger level, higher level problem, which is not a subproblem, and then compute your optimal solution, and then you could also construct your optimal solution. Usually we just do these three steps because usually we want to find the optimized value which the optimal solution can give, but we do not want the optimal solution which gives that optimized value. We usually just care about what the optimal value is, not the solution which gives that optimal value. And today, I think today is going to be a very abstract chapter because, I mean, it is in the name, elements of dynamic programming. That is pretty nice, I guess. Hello, let's go. Yes, today I was late and I'm sorry for that. I had stuff going on. Did you just read CLRS and implement when you learn new concept? Yes, read CLRS and implement new concepts. And like, I'm absolutely very sorry for being late today. Things were happening. Yeah, and now it is fine. So elements of dynamic programming, and I'm going very hard after this because in just yesterday we only did one section, this section in which we solved matrix multiplication, and before that day we only did the rod cutting problem section. Because let's say I give one day to each of these subsections of this chapter, and let's say it is, I guess it is, there are 5 sections in this, so 5 days, and in 5 days my dynamic programming skills would be very improved, and I won't have to think about what dynamic programming is when I see a question that is going to be solved by dynamic programming. So I'm trying to reduce the overhead which it takes to solve a dynamic programming question, and that is cool. Like 7 questions of graphs till now. Yeah. I learning graphs today from CLRS. I have not done graphs from CLRS. I've only done graphs from CACS. But there are a lot of things in CLRS about graphs. Let me actually see advanced graph things and normal graph things. Yep, graph algorithm. There is a whole section about graph algorithms. Elementary graph algorithms, BFS, DFS, topological sort, strongly connected components. I know about components, strongly connected, minimum spanning trees, single source, shortest path, all pairs, shortest path. There is Floyd Warshall in their maximum flow matching in bipartite graphs. It is going to be very interesting when we read this. So yeah, CLRS is amazing. The comprehension is pretty cool. Chapter 20 till DFS or maybe topological sort if I try hard. Yeah, you can read and understand anything if you want, right? It just takes time. And yep, elements of dynamic programming. Although you have just seen two complete examples of dynamic programming method, you might still be wondering just when the method applies. From an engineering perspective, when should you look for a dynamic programming solution to a problem? That is a nice question. In this section, we will examine the two key ingredients that an optimal solution problem, that an optimization problem must have in order for dynamic programming to apply. And those two things are optimal structure and overlapping subproblems. Okay, these two things must be there in an optimization problem, and those are optimal substructure and overlapping subproblems. We will also revisit and discuss more fully how memorization might help you take advantage of the overlapping subproblem property in a top-down recursive approach. Make sense? Using memorization, we can take advantage of the overlapping subproblems property in a top-down recursive approach. Now, what is optimal substructure? That is a nice question. The first step in solving an optimization problem by dynamic programming is to characterize the structure of an optimal solution. That is the first step. Yes, that is like literally the first step. It was written and on page 2, I guess. Recall that a problem exhibits optimal structure if an optimal solution to the problem contains within it optimal solutions to subproblems. That makes sense. So an optimal structure exists when we have a problem. Okay. When we have a problem which has internally optimal solutions to subproblems. And we lost it. Yep, here we were. An optimal structure, recall that a problem exhibits optimal structure. An optimal structure exists when the optimal solution to our high level big problem can only be obtained when we get optimal solutions to subproblems. If our solutions to subproblems is not optimized, then our bigger level problem will not have the optimal solution. That makes sense. I mean, when that is the structure, it is called optimal substructure. When a problem exhibits optimal structure, that gives you a good clue that dynamic programming. Okay, I clicked on that link again. Yep. As chapter 15 discusses, it also might mean that a greedy strategy applies here. Okay, so optimal structure just means that to find the optimal solution to your high level big problem, you need optimal solutions to subproblems. That makes sense. And if that is the case, greedy algorithm might also apply. Dynamic programming builds an optimal solution to this problem from optimal solutions to subproblems. That makes sense. We build optimal solution to our big problem by finding optimal solutions to subproblems. Consequently, you may take care to ensure that the range of subproblems you consider includes those used in an optimal solution. Consequently, you may take care to ensure that the range of subproblems you consider includes those used in an optimal solution. That makes sense. If there is a subproblem whose solution does not actually matter, then I would not find a solution to that. subproblem, it would be like not good. It would be like wasting time. Okay. Consequently, yep, if that makes sense, like, because if I have a big level problem, then, and let's say I can divide this into these parts, and this is a example, and I don't even know where this would be the case, but there must be cases when I want to find the optimal solution to this bigger problem. I only need optimal solution to this part, 1, 2, 3, 4. To find out the optimal solution to this whole thing, I would only require optimal solution to these three parts, to the second part, to the third subproblem, and to the fourth subproblem. And the solution for the first one does not actually matter. And this is just an example. And I don't even know where this would apply. But if there is some case in which where something like this applies, where finding the optimal solution to the bigger problem does not depend on some subset of the subproblems, then I do not want to find out the answer for this subproblem whose solution does not depend for the overall optimal answer. And I would only find optimal solutions to these subproblems which do affect the optimal solution to the overall problem. That makes sense, I guess, but I don't know how this case would apply, where something like this would be. Anyways, here, optimal structure was key to solving both of the previous problems in this chapter. Yes, that makes sense. In the rod cutting example, when we had a rod of length n, we said that, let's say we do not cut the rod, what is the price at that point? It would be Pn, and let's say we cut the rod at this location 1, then we cut the rod at this location 2, or we cut the rod at any random location I, and then if I cut the rod at this location I, what is the best optimal way to cut this left half whose length is I, and what is the best optimal way to cut this right half whose length is n minus I, and what would be the combined cost of these two, which would be, let's say, R, that is the best way to sell a rod of length I, and R, which is the best way of to sell a rod of length n minus I. Add them together, and that would be the best way to sell a rod which you cut at this location I. And then we iterate I from 1 till here, n minus 1, and we take the maximum value between them. But the thing is, the main optimal substructure thing is that when we are cutting the rod at this location, we want the optimal solution for this part, for this subproblem, and we want the optimal solution for this subproblem. And that is cool. That makes sense. That is what we call an optimal substructure. And in the matrix chain multiplication question also, we had matrices, a bunch of them, quite a bunch of them. And we were saying, let's multiply matrices on this side and on this side. What would be the number of scalar multiplications on this side? What would be the total best possible number of scalar multiplications on this side when we are multiplying matrices on left here and on right here? And when we will get some matrix from this side, and we will get some matrix, let's call it 2 5 from this side, and then we will multiply these two, and that would involve some x amount of scalar multiplications. So let's call this index I. So if we are multiplying all the matrices if we are finding the best possible number of scalar multiplications on all the matrices from A1 till AI inclusive, and best number of scalar multiplications from AI till AN, the last matrix. Here AI is not inclusive, AN is included. And then we will multiply, this thing will get some matrix, this thing will also return us some matrix, and we will multiply those two matrices, and that would involve some amount of x amount of scalar multiplications, and that would be the total number of scalar multiplications if we split this matrix product at this I location, and we were just then iterating this I from left part, and the leftmost matrix has the index 1 till the rightmost matrix minus 1, n minus 1. And at each step, let's say our I was here, we want the best amount of scalar multiplications on the left side here, and we want the best amount of scalar multiplications on the right side here. So again, this problem exhibits optimal substructure. That is the optimal solution to the higher level. This whole problem requires optimal solution to this smaller problem on the left and optimal solution to this smaller problem on the right, and that is optimal substructure. Or when you resume the CP sheet again after I read some things, and yeah, after I guess after this dynamic programming thing, when I complete this dynamic programming section, has all the CP resources in 5 icons. Yep. This is CLRS. Bro, you studied randomized algorithms? Yeah, yeah. I watched Eric To's video in which he said we can use, yeah, not like with full brain capacity, but in that Eric To's video, he said if you are tossing a coin, tails or heads, what is, how many times do you have to flip this coin when you would be almost guaranteed to have at least one tail? And it was about if you flip the coin 20 times, the probability that you get no tails when you flip the coin 20 times would be 1 power 1 by 2 power 20, which is a big number. Yeah, which is about a million. So this would be 1 upon 10 power 6 about ish. So if you flip a coin 20 times, the probability that you do not get any tails is 1 in a million, which is very low. It is not precise, but it is very low. So you are almost kind of guaranteed to have at least one tail in this interval. And yeah, something like that. I don't know specifically about randomized algorithms, but they are something like this. And yep, these things are amazing. Concrete mathematics is pretty cool. If you just read the first chapter in concrete mathematics, it is pretty amazing. It has Tower of Hanoi, lines in a plane. I've read these two things and they are pretty cool. They are talking about first you find a recursive formula, then you convert that recursive formula into a closed form formula, and you prove that your recursive formula is the best solution, and also your closed form formula matches the recursive formula using induction. And yeah, at some point I will make a video on these topics, and that would be cool. Now back to this thing, optimal structure, and I messed up. These lines are links. So if I click on something like this, I go to that page. Not yet. It is mostly in recursion. Yep. Concrete mathematics is mostly in recursion. It says in the introduction that most of the book is going to be based on how to convert a recursive formula into a closed formula, and that is nice. But I've only read I've not even completed the first chapter. I've only read those two sections of the first chapter, Tower of Hanoi and Lines on a Plane. That was cool. And now, yep, optimal substructure was key to solving both of the previous problems in this chapter. That makes sense. And yes, we just saw that it was actually the key. And yep, in section 14.1, we observed that the optimal way of cutting up a rod of length n, if Serling Enterprises makes any cuts at all, involves optimally cutting up the two pieces resulting from the first cut. Yes. In section 14.2, we noted that an optimal parenthesization of the matrix chain product AI from AI till AJ that splits the product between AK and AK plus 1 contains within it optimal solutions to the problem of parenthesizing AI till AK and then AK plus 1 till AJ. That makes sense. That is what we saw here. When we want to solve our higher level problem, we want the optimal solutions to those subproblems on which that higher level problem depends on. That is optimal substructure. You will find yourself following a common pattern in observing optimal structure. You show that a solution to the optimal that a solution to the problem consists of making a choice, such as choosing an initial cut in a rod or choosing an index at which to split the matrix chain. Making this choice leaves one or more subproblems to be solved. Wait, you show that a solution to the problem consists of making a choice. Okay. That makes sense. That is true. That is true. The dynamic programming questions that I have solved till now, they involve making a choice, such as choosing an initial cut in the rod cutting example or choosing an index where to split the matrix chain. Okay, making this choice leaves one or more subproblems to be solved. Yes. So first, there is a choice. Okay. You suppose that for a given problem, you are given the choice that leads to an optimal solution. Yes, among all the choices that are present, one of them has to result in an optimal solution. That is true. You do not concern yourself yet with how to determine this choice. You just assume that it has been given to you. That makes sense. That makes sense. We just say, first of all, we say that there are a number of choices, and when we make those choices, our bigger problem is divided into subproblems. And we suppose that one of those choices results in an optimal solution. But first of all, we do not concern ourselves with determining which choice results in the optimal solution. We just assume that one of these choices is going to result in an optimal solution. Okay, that is very, very true. Even we can see this even in the coin change problem. Given this choice, you determine which subproblems ensue and how to best characterize the resulting space of subproblems. Given this choice, you determine which subproblems ensue and how to best characterize the resulting space of subproblems. Okay, so we first let's go with the coin change problem. We have coins 1, 3, 4, and we want to get to 6. Greedy will not work here. Greedy will return 3 coins if we are finding out the minimum number of coins to get to this sum of 6. Greedy will return 3 if you are taking the biggest coin, but the actual answer is 2. To get to 6, we can choose 3 plus 3. And when we want our sum to be equal to 6, we have 3 choices. We could either choose 1 as the last coin, we could choose 3 as the last coin, or we could choose 4 as the last coin. And we are assuming that one of these choices is the correct one. We are assuming that. And based on this choice, we break this bigger problem into a subproblem. So when we choose 1 as our last coin, our problem breaks down to a subproblem where we are finding out the best solution to get to 5. And when we choose 3 as the last coin, our subproblem breaks down to 3. And when we choose 4 as the last coin, our subproblem broke down to be 2. That makes sense. So we characterize, given this choice, you determine the subproblems ensue, which subproblems ensue, and how to best characterize the resulting space of subproblems. So given these choices, first we made the choice of 1, then 3, and then 4, and making the choice of 1, this was our subproblem. Making a choice of 3, this was our subproblem, and when we chose 4, this became our subproblem. And now again we have 3 choices. We could choose to get to a sum of 5, we could choose 1. To get to a sum of 5, we could choose 3, or we could choose 4. And this makes the subproblem 4, this makes 2, and this makes it 1. And here, for this we can say it takes 1 coin. For this we can directly say it takes 2 coin. And for this, let's say we can actually say that to get to a sum of 4, we can choose 3 and 1, and that would be the best solution. Okay, so we said there are a bunch of choices, and when we do make a choice, what would our subproblem be like? When we do make a choice, what would our subproblem be like? And when we do make a choice, what would our subproblem be like? Here it is 2. So to get to a 2, we need 2 coins of size 1. And to get to 3, we can directly get to 3 using a coin of size 1. So here the solution is 1, and we got, I mean, okay, so I messed up saying which part is the problem and what is the solution. They are all mingled up, but the thing is, when we choose 3 as our last point, the answer came out to be 2. When we chose 1 as our last coin, the best answer came out to be 1, 2, 3. And when we chose 4 as our last coin, the best answer came out to be 3. And among these choices, when we chose 1, when we chose 3, when we chose 4, the best answer is given to us when we chose 3, which is 2. That would be our solution. That makes sense. Hello. Do you prefer any sort of music while studying? Nope, not generally, because if I'm listening to music, I'm not actually studying, I'm listening to music. But while coding, sometimes I do, while solving questions, sometimes I do listen to music, like Team Impala. Team Impala is pretty nice. Okay, so we say we have a bunch of choices and we make choices. You show that the solution to the subproblems used within an optimal solution to this problem must themselves be optimal. You show that the solution to the subproblems used within an optimal solution to the bigger problem must themselves be optimal by using a cut and paste technique. You do so by supposing that each of the subproblem solution is not optimal and then deriving a contradiction, in particular by cutting out the non-optimal solution to each subproblem and pasting it the optimal one. You show that you can get a better solution to the original problem, thus contradicting your supposition that you already had an optimal solution. If an optimal solution gives rise to more than one subproblem, they are typically so similar that you can modify the cut and paste argument for one to apply to others with little effort. Okay, so now the question is, what they are trying to say in the book is, when we, let's say, our coins are 1, 3, and 4, and let's say our bigger high level problem is this. We want to get to a sum of n using as few coins as possible to get to a sum of n. So here we have three choices. We could use 1 as our last coin, we could use 3 as our last coin, or we could use 4 as our last coin. Maybe I should not write it this here. I should write these coins here. These green colors represent coins. So when I choose 1 as my last coin, the subproblem that I have to solve is n minus 1. When I chose 3 as my last coin, when I chose 1 as my last coin, subproblem is n minus 1. When I chose 3 as my last coin, subproblem is n minus 3. When I chose 4 as my last coin, the subproblem that I have to solve is n minus 4. Now here, how do we prove that unless we find the optimal solution to these subproblems, we will not get an optimal solution to our main problem? We prove it by contradiction. Let's say we got x as our optimal solution to get to a sum of n, and to get to that x, we solved one of these subproblems in a non-optimal way. Let's say this subproblem n minus 3, the solution that we used to get to x had used some m amount of coins. But let's say by contradiction, let's say this m is not optimal, but an actual answer we could have used m dash amount of coins to get to a sum of n minus 1. And we are saying that m dash is more optimal than m. That is, m dash uses fewer amount of coins to get to a sum of n minus 3 compared to m. But to get to this solution of x, we used this m amount of coins and not m dash. But we are saying here, to get to a sum of n minus 3, this m dash is more optimal. Therefore, this solution could have used fewer amount of coins, and the solution we could say is off by m minus m dash. M is higher, m dash is lower, and we could have used m dash amount of coins to get to n minus 3. And this solution x, which we supposed is optimal, is not optimal because this solution x has m minus m dash amount of extra coins, which could have been avoided if we had chosen m dash optimal solution for n minus 3 subproblem. Therefore, to get to an optimal solution for this problem, we need optimal solution for this subproblem. And I hope that makes sense. I just hope that makes sense. So that is why by contradiction we can say. And how is this contradiction? Because we used m to get to a solution of x. Let's say we used x, we got to x dash using a solution to this subproblem n minus 3 m dash. M dash is more optimal solution to this subproblem n minus 3. And using that m dash, we got to a solution of x dash. And x dash is going to be lower than x, since m dash uses less amount of coins than m. Therefore, x dash is more optimal than x. Therefore, by contradiction, we should not have chosen m, which is an unoptimal way to get to a sum of n minus 3 or any subproblem. Therefore, to get to a better solution for any of the given subproblems, we should choose or find out the optimal solution to the subproblems themselves. And that, I think, makes sense. Conversely, or yeah, that is what we do in this part. Cut paste. And yep, to characterize the space of subproblems, a good rule of thumb says to try to keep the space as simple as possible and then expand it as necessary. For example, the space of subproblems for the rod cutting problem contained the problems of optimally cutting up a rod of length I for each size I. This subproblem space worked well, and it was not necessary um, to try a more general space of subproblems. Okay, so a space of subproblem is the space which has all the subproblems which we are going to solve. And a good rule of thumb is to exclude from that space general topics and only have subproblems which we are going to use to find optimal solution to our bigger problem. That makes sense. That makes sense. For example, in the rod cutting example, we had a rod of size n, and the space of subproblems, the subproblems which we are going to solve involved, let's say r I returns the best possible way to cut this rod of size I. This thing we limited I to be equal, to be greater than 0 and less than equal to n. We limited I to this size. I would therefore belong to 1 till n inclusive, and this is belong. I belongs to this set from 1 till n. And yeah, so we are not using any general concepts here where we are saying we want to find the answer for Ri, where I ranges from 0 till 10 power 6 or something, because we do not need that. We only need I to go up till n. So we reduced our subproblem space. That makes sense. That makes sense. I mean, while we are solving the problem, these things seem obvious, but a lot of thought goes into these things. And that is good. Conversely, suppose that you tried constrained the subproblem space for matrix chain multiplication to matrix products of the form this. As before, an optimal parenthesization must split the product between ak and ak plus 1 for some k between 1 and j. Unless you can guarantee that k always equals j minus 1, you will find that you have subproblems of the form from a1 till ak and then ak plus 1 till aj. Moreover, the later subproblems does not have to form 1 to j. They might not begin from 1. To solve this problem by dynamic programming, you need to allow the subproblems to vary at both ends. Yes, that makes sense. That is why in this thing, in the matrix chain multiplication, we had to use a 2D matrix because the subproblem size was bigger. But in the rod cutting example, we got our work done by only using a single dimensional vector. But in the matrix chain multiplication, vector vector of vector of some type T, that is what we used in matrix chain multiplication, and the writing is amazing, MCM. Yep, because we had to vary the starting position L and also the ending position J at both ends. That is, both I and J need to vary in the subproblem of parenthesizing the products AI and AJ. Optimal substructure varies across problem domains in two ways. Okay, before moving this part, ready for the contest today? Yes. Good afternoon. Hello. And yep, the contest, I will be giving it unrated because it is division 4, and in division 4 a lot of people cheat. So I do not want my rating to just be like stocks in a market, like this thing, activity monitor. I don't want my rating to just go down to hell. So this will be unrated. And it would be fun. I think this would be my first Division 4 contest, and that is, let's see how it goes. And I thought no one gives Division 4, only people who have newbie and pupil rating, they give Division 4 contests. But then I saw the list of the people who were giving Division 4 today, 1050, this thing, wait, not this one, Division 4, and not registered friends, all registered. And if we sort this by rating, LGM are giving Division 4 contests. So that is cool. And I guess they will be able to solve this in less than 30 minutes at max. At max, they will take less than 30 minutes. That will be cool. And what do we have here at home? Do not have a point of rating. Only this is going to be rated if our rating is less than 1400. That is fine. ICBC rules, there will be 7 problems and we will solve them in 2 hours and 15 minutes. That is cool. And we also have hi here somehow. Cool. Now back to this. Okay, so that is something that I haven't thought about consciously. When I have a problem, let's say x, and xn is my higher level subproblem, the problem that I have to solve, xn, and I can divide it into subproblems x1, x2, dot 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 till xn, and I'm just using this notation right now, xn minus 1. If that is a thing, this is linear, but this, the factors which I use to define the solution for a subproblems, here in this case, it is only one factor, but in some cases, the factors could be two, m comma n. Now, to define an optimal solution, it depends on two factors. And if my problem depends on two factors, then the problem space is going to be two-dimensional. That makes sense. This is like knapsack and coin change problem, because in knapsack, or let's say in coin change, to define, to get to a solution, we need to know what was the last coin that we used, let's say coin CI, and also what was the sum S, and depending on the coin that was used and the sum that was used, we define a subproblem. And similarly, in knapsack, we say we have a weight W, and to get to that W, we used some element. Let's say we have elements E1, E2, E3, which we could add to our knapsack, and we used element E3 to get to this sum, to to get here. And X here is a function which takes in two things. Shit, I should write it as F W E, and this thing is a subset, and this thing is a integral weight. Okay, so yes, in a knapsack problem, we have been given a higher weight and a set of elements. Let's say E1, E2, E3, E4, for example, right? So a subproblem, what we want the answer for is F W, and let's call this whole set X. Here it means this is the best weight. This will return, let's say, WX. Let's call it WX, and this WX would be the highest value. Let's say in this knapsack problem, this is the weight that we can have, maximum weight, and these are just weights E1, E2, E3, E4, E4. But these should also have values. Let's say these things also have values. Okay, let's define it again. W is the total weight, and the elements have weights W1, W2, W3, and W4, and they also have values which are V1, V2, V3, and V4. And when we define a subproblem, let's say by F W I, and this returns something called X. So here W is the weight that we want to achieve, that we can have adding these elements, and I is the index of starting from the first element, how many elements we are adding to our bag. Let's say if I equals 3, then we are only adding the first 3 elements to our bag, these 3, and W at that point is the weight that we want to achieve when we could only add these 3 elements. So here a subproblem requires two things to be specified: a weight and the number of elements which we are using from our set. So therefore, we can see, since it depends on two things, our sub-problem space is going to be two-dimensional. In one dimension, we will have the weights, and in another dimension, we will have the sets, and that is two-dimensional sub-problem. And when we are solving a question like longest increasing subsequence, in that case, yes, when we are finding in the longest increasing subsequence, our function for subproblem only depends on a singular integer. I mean, if we are trying to solve it using dynamic programming, but we don't have to solve it using dynamic programming, our solution only depends on a single integer, which says in our array of length n, if we are only choosing the first I elements, if we are only choosing those first I elements, what is the length of the longest common subsequence? So here we can say our subproblem space is one dimensional because our subproblem function, this one, only depends on a single factor. That is going to help a lot. One dimensional and two dimensional. So if we can just write down the form of this function, or how many number of factors it uses, we can determine the size of our sample space. And then when we have this defined, the factors on which our subproblem depends on, we can write recursively how this function changes I minus some constant and j minus some constant something something. If we can define our function recursively, we can write the dynamic programming approach. We used this to define our sample space for subproblems, and we used this to write the logic to fill that space of subproblems. That is good. That is actually good. That is good. Hello. Hello, bro. First time here. Can you tell about yourself and what are you studying and from where? I'm from Uttar Pradesh and I'm studying right now competitive programming. I'm not trying to, but I want to get to a rating of 2000 in competitive programming, and we have to study a lot to get there. That is cool. And the main purpose of this channel is to show that you can see that I'm not very smart, but if I work hard, I will be able to get to a rating of 2000. And the main purpose of this channel is to show that it is possible. If you just work hard consistently, you will be able to do things that you do not think you could do. So that is the purpose of this channel. And if I could help you in that way, in making you realize your potential, I would be happy, a little bit more happy than I am. So that is the main purpose. And yeah, so yeah, sample space of subproblems. Optimal structure varies across problem domains in two ways. Okay, optimal substructure varies across problem domains in two ways. How many subproblems an optimal solution to the original problem uses? How many choices you have in determining which subproblems to use in an optimal solution? This is very cool. This is very cool. This is like stating all the things which I have seen implicitly till now. So here they are saying that optimal substructure, yes, the spelling is correct. I think it is correct. I hope so. Optimal substructure depends on the number of subproblems and the number of choices available. That is very true. That is actually very true. That is actually very true. Optimal substructure depends on the number of subproblems we have and the number of choices. If we go with the coin change problem to get to a sum of n, we have at any point cn number of choices. That is the number of choices, the number of coins that we have at any point, and the number of subproblems coincidentally in the coin change problem also is cn, because making one choices results in one subproblem that we have to solve. So in this case, the number of subproblems and the number of choices is the same in the case of coin change problem. But let's say for other, yes. For other problems like the rod cutting problem, if our rod is of size n, here we can cut our rod at the smallest index 1 or at the largest index n minus 1, or we could not cut the rod at all. So in total we have n choices. Here in total we have n choices, but each choice results in two subproblems. Subproblem of size here 1 till 1 till I. This is the size of one subproblem, and the size of another subproblem would be I till n. So here the number of choices is n, but the number of subproblems is 2n, because making one choice results in two subproblems. So that is optimal structure. But we know for a fact that a lot of these subproblems are going to overlap. And that is overlapping structure where we use memorization or tabulation. So that is cool. That is cool. That is cool. So there are two ways, two factors. Optimal structure varies across problem domains in two ways. How many subproblems are going to be created here, which is n minus 2, and the number of choices available at a given problem, which is n. In this case, in the rod cutting example case. And same would be, yo, hello. My LinkedIn ID, it is just my name. I think you will be able to find it if you search. And I mean, why would you need my LinkedIn? It is empty. I don't post anything there. In the rod cutting problem and optimal. And Eric, did you see this? This is very interesting. Maybe, I guess you knew this already. When we are solving a problem using dynamic programming at any point, let's say when our problem size is n, we have a number of choices, and we have a number of subproblems which result from making a particular choice. And in the coin change problem, the number of choices that we get at a number n is the number of coins we have, but here the number of subproblems that we have to solve is also equal to cn, the number of coins that we have. So here the number of choices and the number of subproblems is same, literally the same thing, C and Cn. But in a question like the rod cutting one, here we have n number of choices. That is, we could cut the rod at n minus 1 places, and one choice is of not cutting the rod at all. So n minus 1 places to cut the rod and one choice to not cut the rod. In total, n choices. And making one choice results in two subproblems. Subproblem on the left and subproblem on the right. So in total, since we have n choices, we will have 2n subproblems, like 2n minus 1, because when we are not cutting the rod, we don't have any subproblem. But anyways, this is the subproblem size, and that is cool. That is cool. That is cool. It is like explicitly stating what we were seeing uh, implicitly till now. Hello, nice stream. What book you are using? We are using CLRS for algorithms. I think your subproblem for coin change is not CN, is N, not CN. Okay, here we are not, okay, it would be N, the number of subproblems would be N if we have a choice, if we have a coin of size N, of size 1, because then you would have N minus 1 as a subproblem and N minus 2 as a subproblem till 1. But here I think in the book, they meant at one particular level, when our problem size is n, at that level, there are Cn subproblems, right? But in those Cn subproblems, we are not looking at how many subproblems do they internally depend on. We are just saying on how many subproblems does this n problem depend on. And yep, so at one particular level, at one particular layer, how many subproblems does a given problem depend on? That is Cn. Yo, what's up? How are the preparations going on? I hope cool. At 10 p.m. It is a long time. And I looked up something. Kiosk kitne? And I won't tell you what the meaning of that is. You can look it up. But remember, kiosk kitne? And back to this. In the rod cutting problem, an optimal solution for cutting up a rod of size n uses just one subproblem. Yes, shit. Because yeah, my bad, my mistake here. When we were cutting a rod at one particular index I, when we were cutting the rod at one particular index I, we were saying that we are only going to cut we are only going to find the optimal way to cut the right side, and we will say we are not cutting the left side. That was like an optimization which we made in that. So I guess it would be around 3 a.m. there. In the rod cutting problem, yeah. So just one subproblem. When we cut the rod at an index I, only the right side is the side that we are finding the optimal solution to. And we are saying that we are not cutting the left side, because that would also result in the same optimal solution for the higher level problem. And the problems that we are trying to solve is reduced by half, because we are not solving for the left side. Yep, but we have to consider n choices for I in order to determine which one yields an optimal solution. Yep, we have n choices, and each choice results in one subproblem. Matrix chain multiplication for the subproblem chain serves as an example with two subproblems and j minus I choices. Yep, two subproblems for each choice, and we have in total j minus I choices. For a given matrix AK, where the product splits, two subproblems arise, parenthesizing the left side from I till k and parenthesizing the right side from k plus 1 till j. And we have to solve both of them optimally. Yes, because if we do not solve them optimally, we saw by contradiction that our the solution to our higher level problem will also be unoptimal. But we are looking for the optimal solution. Informally, the running time of a dynamic programming algorithm depends on the product of two factors: the number of subproblems overall and how many choices you look at each subproblem. That is true. Informally, the running time of a dynamic programming algorithm depends on the product of two factors: the number of subproblems overall. Yes. Okay, so we are actually calculating the total number of subproblems. Yes, kiosk hai na. It is take care. Okay, 12095. Okay, I will not not right now though, but is here. Let me put it at some place. Sorry, why sorry? It is fine, totally fine. Informally, that is very informal. The running time of dynamic programming algorithm depends on the. Okay, so we are here considering the total number of subproblems, which is very similar to what Eric said before. The total number of subproblems, not the subproblems we have to solve at one particular level. So let's say we have n number of subproblems, which we do in coin change. No, I think in coin change, if n is the maximum amount that we want to get to, then what is the highest level of denomination that we have, the smallest level of denomination that we have, that would define a lot of things. Yeah, we can say roughly it is n. We can roughly say it is n. Yeah, we can roughly say that we want to get to a sum of n. And to get to a sum of n, there will be n subproblems. And at each level, we will have Cn subproblems. We will have Cn choices. So the total running time approximately, informally, is n into Cn, n into Cn. And in CSES, coin combinations, minimizing coins. There are 3 coins. This is our the size n. At max, we could have 100 choices, and the maximum sum that we could have, the target sum, is 10 power 6. So that results in a time complexity of 10 power 8, which is just doable, just doable. And why did I got all of these wrongs? That is bad. I think I was not seeing, I was not considering for the fact that I might never be able to reach the sum that was given. So informally, that is the running time. That is it. Yep, the number of subproblems overall, and how many choices you look for at each subproblem. In rod cutting, we had n subproblems. Yes, n subproblems overall, and yes, at max n choices. So the time complexity would be n square. That is a very shorthand way of finding out the time complexity in dynamic programming, because it is not very straightforward. Matrix chain multiplication. Okay, let's not look at this. Let's calculate it ourselves. When we add n matrices, the total number of subproblems, a subproblem f I j depends on two things, I and j. I can at max, let's say, iterate from 1 till n, and j can also go from I till n. And we can boldly, or like around, and this would be around n square, but more specifically, this would be n into n plus 1 by 2. Like this would be a triangular number like this, but we can write it in big O notation as n square. So there would be approximately n square subproblems, and at each subproblem we have to go through, we have n choices at max. At max we have n choices, n minus 1 choices, but we can write it as n. So the total running time would be n cube, which is very bad. Shit. Is it actually? It is n cube. Multiplication had n square subproblems overall, and each had at most n choices, giving an O of n cube running time. Actually, a average, not worst, but average. No, this is I guess best case omega. Running time by exercise 14.25. Yep. Usually the subproblem graph gives an alternative way to perform the same analysis. Yes, this is analyzing. And we could also do the analysis using the subproblem graph method. Each vertex corresponds to one subproblem, and the degree of a vertex says how many choices we have at a given level. Yep, that makes sense. For coin change, when we have coins 1, 3, 4, and we want to get to a sum of 6, let's say this n denotes a subproblem of size n where we want to get to a sum of n. So to solve 6, we could also solve f5, a subproblem of size 3, 4, a subproblem of size 3, a subproblem of size 2, a subproblem of size 1, and 0. And this thing depends on 5 when we chose 1, and also it would depend on 3 when we chose 3, depend on 3, so 1, 3, and when we chose 4, this would depend on the subproblem of 2 when we chose 4, and this thing 5 would depend on 4 when we chose 1, and you can say like this: 1 for all of them, 1, 1, 1, and for 3 when we chose 3, this thing would depend on 2. When we chose 3 here, this thing would depend on 1. When we chose 3 at this thing would depend on 0. And we cannot choose 3 when we have a subproblem of size 2 and not here. And when we choose 4 here at 5, this would depend on 1, 4, and this would also depend on 0. So here the maximum degree is this for the node of size 6 and the node of size 5 and also the node of size 4. The maximum degree is 3, and the number of subproblems is 1, 2, 3, 4, 5, 6, 7, which is almost like n, and this 3 is the number of coins that we have. So in total, the time complexity is O of n Cn. Informally. Each vertex corresponds to a subproblem, and the choice for a subproblem for all the and the choices for a subproblem are the edges incident from that subproblem, the edges that are going out from that subproblem. That is the number of choices available there. Recall that in rod cutting, the subproblem graph has n vertices and at most n edges, at most n edges per vertex, yielding a time complexity of n square. Running time. For matrix chain multiplication, if you were to draw the subproblem graph, it would have n square vertices. That makes sense. And I think we actually did make a subproblem graph yesterday. Yep, B2 Bomber, Spirit. This is a subproblem graph for matrix chain multiplication when our n was equal to 3. Here our n is equal to 3. This has 1, 2, 3, 4, 5, 6 vertices, which I guess we could say is very similar to 3 cube, which is 9, 1, 2, 1, 2, 3, and 2, 3. Yeah, at max. So the number of vertices is not going to be greater than n square, and the number of edges at each location tells us the number of subproblems that need to be solved for this particular subproblem. That is cool. And yep, recall that in rod cutting, it was n square. For matrix chain multiplication, if you draw the subproblem graph, it would have, so they are not saying it will have exactly n square, but average, best case, worst case, n square. I don't know the asymptotic notation, I will have to read upon it. Vertices, and each vertex would have degree at most n degree. Here I messed up a little bit in drawing the edges, because this one does not directly depend on this one. Yep, this one does not directly depend on this one. I messed up in drawing the edges, and also not on this one. Oh, yeah, it does depend on this one, and it also does depend on this one, but it doesn't depend on this one, the subproblem of size 1, 3. And here the time complexity would be about n cube. That makes sense. 096, I said by mistake. Oh, okay. Man behind B2 Bomber Designs is Jatin. Lord. Yep. Shit. They got me. They got me. Shit. Don't tell the FBI. Kash Patel. Don't tell him. Dynamic programming often uses optimal substructure in a bottom-up fashion. Yes, it does use optimal substructure. It has to has optimal substructure, but we don't have to always apply bottom-up fashion, because applying bottom-up fashion is a bit harder compared to recursion, but bottom-up is faster because of no function calling overhead. So that is good, because we are only using loops in bottom-up instead of writing function calls. That is, you first find optimal solutions to subproblems, and having solved the subproblems, you find an optimal solution to the problem. And reading this is very fun, because till this point I have been solving dynamic programming questions, and every time I see a dynamic programming question, I have to invent the methods, because I hadn't read any material. And now reading some material gives me some hope. No, not hope. Hope is not the right word. It gives me some structure to think about dynamic programming. And these things I have been through. Yep. So in bottom fashion, we first solve the subproblems, and having solved the subproblems, you find an optimal solution to the problem. And this makes so much sense now. After solving questions, this makes so much sense. Finding an optimal solution to the problem entails making a choice among subproblems as to which you will use in solving the problem. That is also true. The cost of the problem solution is usually the subproblem cost plus a cost that is directly attributable to the choice itself. Yeah, the cost would depend on the cost for solving the subproblem plus the cost of making the choice. CH is choice. Yeah, that makes sense. For making the cost for making the choice, and the cost for solving the subproblems. That makes sense. Finding an optimal solution to the problem entails making a choice among subproblems as to which problems you will be using to find solution to your problem. To find optimal solution to your problem. The cost of the problem solution is usually the subproblem. The cost, yes, is usually the subproblem cost plus a cost that is directly attributable to the choice itself, plus the cost that is directly attributable to the choice itself. In cutting and rod cutting, for example, first we solve the subproblems of determining optimal ways to cut rods from of length I, where I ranges from 0 to n minus 1. So first we solve for all of these subproblems, and then we determine which of these subproblems yield an optimal solution for rod of length n by going through all of them. In this particular example, we have to go through all of them. But when we are solving something like coin change for a sum of 6, when we have coins 1, 3, 4, the solution to this problem only depends on solution to 5, to 3, and to 2. These are the only subproblems on which this thing depends on. And these internally depend on other subproblems, but this one, the problem only depends on the solution for these three things. The cost attribute to choice itself is the term pi. Wait, I missed something. Yep. First, we solve the subproblem of determining optimal ways to cut up rods of length I, where I ranges from 0 to n minus 1. And then we determine which of these subproblems yield an optimal solution of a rod of length n. And in determining so, we, in this particular case of rod cutting problem, or in the dynamic programming implementation for cutting up a rod, it depends on all the subproblems, which is not a general case. It generally does not, generally our solution to the problem does not depend on all the subproblems. It is particularly the case for the rod cutting problem, but in general, it is not the case. In the coin change problem, our optimal solution to our problem only depends on 3 subproblems. In this particular instance of the coin change problem, it generally depends on Cn subproblems, which is the number of coins that we have in the coin change problem. So that is the case in general. And then we determine which of these subproblems yield an optimal solution of rod for a rod of length n using equation 14.2, which was at some point somewhere the cost attributable to the choice itself is the term pi in the equation. In matrix chain multiplication, we determine optimal parenthesization of subchains of this thing. And okay, this thing, what is this? The cost attributable to the choice itself is the term pi. Okay, okay, shit. Okay, that makes sense. The cost attributable to the choice itself is the term pi. Okay, where is the 14.2 equation? We have to get to the bottom up to this of this thing. 14.2, 14.2. Yep. Ah, that makes sense. That makes sense. That makes sense. That makes sense. And why does it make sense? Let me show you. Let me attempt. So wait, we were here. Yes. So yes, that makes a lot of sense. As you said before, I gotta leave here again after I return to states. Yep. All the best. Have fun. And yep, have fun. Our optimal structure depends on two things. It has two things which can vary our optimal structure. The number of choices. Let's actually write number of choices instead of just choices. Number of choices and the number of number of subproblems. These are the two things that this thing depends on, and that our optimal structure can vary upon. And when we want to calculate what the cost of making a particular choice is going to be, it is usually, like they said in the book, it is usually the cost of subproblem, that is one thing, plus, just plus the cost of choice. And that is so true. That is very, very true. That is actually pretty insightful. So when we make a particular choice, for example, in the coin change problem, when we want to get to a sum of n, and we have some choices C1, C2, C3, C4, where C1, C2, C3, C4 are the coins that are available. So when we want to get to a sum of n, we have four choices. In this case, C1, C2, C3, and C4. And C4. When we have these choices, let's say I made this choice, then what would be the cost associated, the total cost associated with this choice? The total cost would be the cost, let's have a cost function, cost for getting to a sum of n minus c1, first of all, plus 1. Why 1? We are adding 1 because we did choose this coin c1. Due to that fact, we have to add 1 to our overall cost for this choice, and same goes for this, and for this. And in this example, the cost of choosing any of these coins, C1, C2, C3, this internal cost for getting to a smaller sum is going to be different in all of these, but this cost, which is attributed to the fact that we are making a choice, is going to be same, because at all of these choices, whenever we are making any of these choices, we are using only one coin. So the number of coins to get to a sum of C of n minus Ci, those number of coins, those coins, plus one coin, which we just chose. So in this case, the cost that is attributed to the choice itself is same, but it can be different in different cases. For example, in the rod cutting problem, when the rod is of size n is the size of the rod, whenever we make some choice at index I, this thing, we are saying we are not cutting this part, but we are only cutting this part. And the cost of this choice is going to be, first of all, the cost for this part, which is, let's say we have a cost function again, Cn minus I, the maximum cost for this part, plus the cost for this part, which is Pi, where P is a vector which has the price for a rod of length I, because we are not cutting this part, we are only cutting this part. So this part we are selling as it is by taking its direct price price of rod of size I from the vector P. So here the cost of making a particular choice is different for all the i's that we have. We have our vector P where Pi has the cost, some x cost xi, which is the cost for a rod of size I. And in this case, for every I, the cost for making that particular choice is different, unlike the coin change problem, where the cost for making a particular choice was same. It was 111 for all the choices, but here it is Pi. It is different. That is cool. That makes sense. That actually makes sense. There is a cost associated with the subproblem and a cost associated with making that choice itself. So we have seen quite a bit till now in this chapter. That is a lot to take in, but slowly we will see quite more. Let's go. Let's not stop. Chapter 15. Shit, AHO. AHO. Hmm. I've heard that name before. Yep, we were right here. Chapter 15 explores greedy algorithms, which have many similarities to dynamic programming. In particular, problems to which greedy algorithms apply have optimal substructure, that is optimal choice. Optimal solution to the problem depends on optimal solutions to subproblems. One major difference between greedy algorithm and dynamic programming is that instead of first finding optimal solutions to the subproblems and then making an informed choice, greedy algorithms first make a greedy choice, the choice that looks best at the time, and then solve a resulting subproblem without bothering to solve all possible related smaller subproblems. Surprisingly, in some cases, this strategy works. That is cool, and we will know more about greedy algorithms when we get to greedy algorithms, which is the next chapter. Subtleties. You should be careful not to assume that optimal substructure applies when it does not. Okay, and like that is like seeing things when they do not exist. Consider the following two problems whose input consists of a directed graph. Consist the following two problems whose input consists of a directed graph. Okay, V the vertices and E is the edges. Unweighted shortest path. Find a path from U to V consisting of the fewest edges. Such a path must be simple, since removing a cycle from the path produces a path with fewer edges. Yep. Unweighted shortest path. That is one problem, and I think it has optimal service structure because at every node we have a bunch of choices, and that results in a bunch of subproblems, and we have to solve those subproblems to find the optimal solution to our bigger problem. Okay, unweighted longest simple path. Longest. Okay, so in both the cases, we are optimizing for the length of the path, but the longest is messed up because there could be loops and you can go around a loop infinite number of times. Does not matter. Unweighted shortest path. Here we want the smallest length, and here we want the longest length. Find a simple path. Simple. Okay, simple path. We cannot make loops from U to V consisting of the most edges without the requirement that the path must be simple. The problem is undefined since repeatedly traversing a cycle creates path with an arbitrarily large number of edges. Yep. So therefore this must be a simple path, and if it is simple path, I guess we can apply dynamic programming. The unweighted shortest problem exhibits optimal substructure. Yes, it does. Here is how. Suppose that u is not equal to v, so that the subproblem is non-trivial. Then any path p from u to v must contain an intermediate index w. Note that w may be u or v. Then we decompose the path u to v into subpaths. From u to v, we'll like to get to w first, and then that would be our first path, and the second path would be from w to v. The number of edges in p equals the number of edges in p1, plus the number of edges in p2. Yes, we claim that if p is an optimal, that is shortest path from u to v, then p1 must be shortest path from u to w. Why? Because if it is not, then by contradiction, we do not have the optimal solution to our bigger problem, and therefore we could have found a better solution to our bigger problem if we had chosen optimal solution to the smaller subproblem. Subproblems are smaller, so we don't have to say smaller subproblems, they are just subproblems. We claim that if P is an optimal, that is shortest path from U to V, then P1 must be shortest path. Why? As suggested earlier, use a cut and paste argument. If there were another path P-1 from U to V with fewer edges than P1, then we could cut P1 and paste P1 dash to produce a path like this with fewer edges than P. This contradicting P's optimality. Likewise, P2 must be the shortest from W to V. Thus, to find a shortest path from U to W, U to V, consider all intermediate vertices W, find a shortest path from U to W and a shortest path from W to V, and choose an intermediate index W that yields the overall shortest path. That makes so much sense. Section 23, that is a graph algorithm right there. Use a variant. Section 23.2 uses a variant of this observation of optimal substructure to find the shortest path between every pair of vertices on a weighted directed graph. So yeah, I mean, this thing was very easy to spot because I had read all of the dynamic programming stuff till this point, so that was easier to spot. And you might be tempted to assume that the problem of finding an unweighted longest simple path exhibits optimal substructure as well. Huh? You might be tempted to assume that the problem of finding an unweighted longest simple path exhibit optimal substructure as well. Yes, it would. Why would it not? Should it does not? After all, if we decompose a longest path into two subpaths, P1 plus P2, then mustn't P1 be the longest simple path from U to W, and mustn't P2 be a longest path from W to E? The answer is no, because they might be overlapping. The answer is no. Figure 14.2 supplies an example. 14.6 supplies an example. Consider path Q which goes to R which goes to T. Path which goes from Q to R to T. Okay, which is a longest simple path from Q to T. Okay, yes, is makes sense. Makes sense. So yes, that is so true. Okay, if we have a graph like this, Q, R, T, S, and all of these are connected like so, Wesley so, a chess player, and like that. Everything is connected. We can go from any one place to any other place. And when we are finding the longest path from this point to this point, if we use our argument by saying, let's find the longest path, let's choose S as the intermediate node and find the longest path from Q to S. The longest path is going to be from Q to R to T and then to S. And that is bad. And then if we were going to find the longest path from S to T, that would be from S to Q to R to T, and size would be 3, and here also size would be 3, and we would get 6 as our answer, but that is wrong. This would essentially return us a path like this. From Q we went, and this resulting path I am representing by brown. From Q we went to R, then we went to T, then we went to S, then we went to Q, then we went to R, and then we went to T. Here the total number of edges is 6, but that is wrong because we are making a cycle. We want a simple path. Makes so much sense. Supplies an example. Consider the path Q to R to T, which a longest simple path from Q to T, which is a longest simple path, because there can be other longest simple paths from Q to T. Is Q to R a longest simple path from Q to R? No. For path Q to S to T to R is a simple path that is longer. Is R to T, from this R to this T, this is the longest simple path from R to T? Nope. The longest simple path would be from R, we go to Q, then we go to S, then we go to T. It is like from R to Q to S to T is a simple path that is longer. So this example shows that for longest simple paths, not only does the problem look optimal, lack optimal substructure, but you cannot necessarily assemble a legal solution to the problem from solutions to subproblems. If you combine the longest simple paths, this and this, we get an illegal substructure like this, which is not simple. Indeed, the problem of finding an unweighted longest simple path does not appear. Oh shit, I misstepped. Wait, 14.6? Nope, we came too far ahead. This is 14.5, you were at 14.3. Right here. Does not appear to have any sort of optimal substructure. So we have to be very careful when we are saying a problem has an optimal substructure and when it does not have an optimal substructure. That makes sense. No efficient dynamic programming algorithm for this problem has ever been found. Shit. For finding the longest path. That is crazy. That is crazy. In fact, the problem is NP complete, which is crazy, which, as we shall see in chapter 34, means that we are unlikely to find a way to solve it in polynomial time. And if you do not know about NP completeness, you can go to my channel. There is a video on NP completeness, and that is fine. That is good enough so that you will be able to understand what NP means, what is N and what is P. Like N by itself is not anything. We have P and NP. P means algorithms which run in polynomial time, and NP means algorithms or problems which cannot be solved in polynomial time. So non-polynomial NP, that is NP. And NP complete is a problem which can be converted into any other NP problem. Yeah, NP complete is a problem which is in the set of NP problems, and it can also be converted into any other NP problem, and we call such problems NP complete problems. Now here, what is the substructure of a longest simple path? Why is the substructure of a longest simple path so different from that for a shortest path? For that is a good question. Although solution to a problem for both longest and shortest paths uses two subproblems, the subproblem in finding the longest simple path are not independent. The subproblems in finding the longest simple path are not independent, whereas the paths whereas for shortest paths they are. What do we mean by subproblems being independent? We mean that the solution to one subproblem does not affect the solution to another subproblem. That is true in this case. It is true. For example, 14.6 of exam figure 14.6, we have the problem finding a longest simple path from Q to T with two subproblems: finding longest simple paths from Q to R and then from R to T. For this, the first of these subproblems, we choose the longest path from Q to R is, we go from Q to S to T to R, which is true. From Q to S to T to R, that is the longest path from Q to R. Yep, which used the vertices S and T. These vertices cannot appear in a solution to the second subproblem, since the combination of these two solutions to the subproblem yield a path that is not simple. If vertex, yeah, so that limits how we are going to find the solution to the second subproblem. Yes, if vertex T cannot be in the solution to the second subproblem, there is no way to solve it, since T required to be on the path that forms the solution, and if we cannot have it on that path, then everything is messed up. And it is not the vertex where the subproblem solutions are spliced together, that vertex being R. Since T required to be path on the second subproblem to form the solution to the second subproblem, and it is not the vertex where the subproblem solutions are spliced together, pasted together, because vertices S and T appear in one subproblem solution, they cannot appear in another subproblem solution. One of them must be in the solution to the other subproblem. However, we cannot have them because we have already used them, S and T. One of them must be in the solution to the other subproblem. However, and an optimal solution requires both to be optimal, but we cannot have them both optimal because they are overlapping. This would break the rules of physics. No, the rules for the question. Looked at another way. What is that grammar? Looked at another way using, okay, let's bear with it. Looked at another way using resources in solving one subproblem. Those resources being vertices render them unavailable for other subproblems. That makes sense. Yeah, sorry, P versus NP. Yep, P versus NP. I think that was not very comprehensive, but that if someone watches it, they will be able to understand what the problem at least is what the discussion is about. P versus NP. What is P? What is NP? P is a set of algorithms which run in polynomial time, and NP is a set of problems which do not have a polynomial time algorithm to solve them. So that is cool. And NP complete, a problem is said to be NP complete if it is in the NP set, and also it can be converted into any other problem which is also in the NP set. I think Sudoku is NP complete. There is no polynomial time algorithm to solve Sudoku. The best time, I guess, is n square, order of n square, something like that. Sudoku is NP in the NP set, and also traveling salesman, of course, traveling salesman is also in the NP set, and the satisfiability problem is also in the NP set, and the satisfiability problem is NP complete. And also this part, this second question here, unweighted longest simple path is also NP complete. NP complete right here, and it will be very fun to read that chapter 34. And to give you a sneak peek, not to give you a sneak peek, but to tell you a little thing, I am learning how to edit videos, and when I'm good enough, I will start making videos which I will be uploading on the channel, and that would be cool. Now back to this thing. Because an optimal solution to the length n includes just one of these subproblem solutions, after cutting on the first piece, independent subproblem is not an issue. Wait. We were about here. Yep. Why then are the subproblems independent for finding shortest path? The answer is that by nature. Okay, the subproblems have to be independent. The subproblems have to be independent. That is, the optimal solution for finding the optimal solution for one subproblem does not affect the optimal solution to another subproblem. That makes sense. The subproblems do not share resources. We claim that if a vertex W is on the shortest path from P, path P, from U to V, then we can splice together any shortest path P1 from U to W and any shortest path P2 from W to V to produce a shortest path from U to V. Because if they were to share resources, it would mean if they were to share resources, this path 1 and path 2, it would mean I am visiting some node in path 1 and I am visiting that same node again in path 2, which would mean I am making a loop, and I could just skip making that loop and get a better solution. So that is why they are independent. We assure that other than W, no vertex can appear in both paths P1 and P2. Why? Suppose that some vertex X, which is not equal to W, appears in both the paths P1 and P2, so that we decompose our path like this, from PU to X and then from X to W, and P2 would be from W to X and then from PX to V. By optimal substructure of this problem, P has many edges as P1 and P2 together. Let's say, right, by optimal substructure of this problem, P has many edges as P1 and P2 together. Many edges as P1 and P2 together. Whatever. By the optimal substructure of this problem, path P has many edges as P1 and P2 together. Okay, let's say P has E edges. Now let us construct a path which has X from U to V, because we have excised the paths from x to w and w to x, each of which contains at least one edges, path p dash, this one is going to be smaller than the path that we got after adding these two paths, which contradicts the assumption that p is the shortest path. Yes, by contradiction. Therefore, they do not have anything in common. They are not sharing the same resources. Thus, we assure that the subproblems or the shortest path problems are independent. That is true. The two subproblems examined. Yep. The two problems examined in section 1 and 2 of this chapter have independent subproblems. In matrix chain multiplication, yes, they are totally independent because of course they are independent. We are not using same matrices in the subproblems. The total set of matrices that we have in those subproblems is different, is independent, literally independent. In matrix chain multiplication, the subproblems are multiplying chains a1 to ak, ai to ak, and then ak plus 1 to aj. These subchains are disjoint. That is a better word than saying they are not same. They are disjoint, so that no matrix could possibly be included in both. In rod cutting, to determine the best way to cut up a rod of length n, we look at the best way of cutting up the rods of length I for I0 to n minus 1, because an optimal solution to the length n problem includes just one of these subproblem solutions. After cutting off the first piece independent of the subproblem is not an issue. I mean, yeah, in the second problem, in the rod cutting problem, literally we are making some choice at some position in the rod has no effect on any choice. Yeah, it literally has no effect on what I can do with the other subproblem. Yeah, because one choice results in only one subproblem. So we do not have contradicting subproblems. Overlapping subproblems. Yes, we did optimal substructure, optimal substructure. Now we have overlapping subproblems. Overlapping subproblems like this, and reconstructing an optimal solution, then memorization, and then a few exercises. Okay, I should not be looking at how much chapter is left because that is bad exercise. That is bad thing. And I'll be right back. I'll have to go to the washroom and I will be right back in a minute. You, I am totally back. So we have done optimal substructure and now overlapping subproblems. And in optimal substructure, there were a few things, few interesting things that we saw. Last was this. Let's, before moving on to overlapping subproblems, let's list them out. Optimal substructure. These 4 points, and then there were 2 points, these two, and then there was the fact subtleties, about subtleties. So there were three things in total, and those three things involved a few things, a few different things. Okay, so wait, not just so. So for optimal substructure, we say for our problem, we have a bunch of choices. Our problem has a bunch of choices, and we say one of them is optimal. One of the choices is optimal. And to solve these choices, we will have sub, that is definitely wrong spelling. We have subproblems. To solve these choices, like when we make these choices, we will have to solve our problem after making a choice will be divided into subproblems. Yep. And to find out which choice is optimal, we have to go through all the choices which are available and to find the cost of a choice. Yes, choice cost. It usually is the sum of cost for that sub problem, cost of subproblem plus cost for making that choice, which seems like recursive because here we said choice cost equals cost of subproblem plus cost of choice. With this, we can write this as overall cost for making a choice is the sum of that sum of cost for the subproblems that emerge as we make that particular choice and the cost for making that choice, which we discussed here in the coin change problem. The cost of choice is same, and in the other example, the rod cutting example, the cost of choice, this part, cost for choice changes. So this is one of the things that we saw right now. And also optimal substructure varies on 2 points: choices available and sub problems required to be solved. These are the two things, and this feels very good to know. Yep, optimal structures can like vary on two factors. One, on the number of choices that are available at some point, and the number of subproblems that would be required to be solved for making that choice. And that is cool. And also there was a fact about sub. Why is my writing so slow? Problem space, subproblem space. It depends on factors defining a problem, it depends on the number of factors that are defining a subproblems. And this thing, when we know the number of factors which are defining subproblems, which are defining a subproblem, it tells us the size of subproblem problem space, or instead of size, dimension would be a better word. Dimension of subproblem space. When we know the number of factors defining subproblem, we can use it to find out the number of the dimension for the subproblem space that we have to solve. And there was one more thing in the optimal structure part. I do not want to look at the notes. I do not want to look at the book. I want to remember it. There was one more thing. Okay, we did the cost part, how we find the cost, that there are choices, then there are problems, and there is the fact about subtleties. Subtleties, where we saw that some problems have non-independent subproblems. Yeah, that is like true. Some problems have non-independent subproblems, and that is one of the subtleties. Yep, there was one more thing in that. Yo, hello, how are you? So that is cool. These are the things that we have read till now, and we also understand what these things mean, so which is even better. These are the things, and there was one more thing there. There was one more thing. Cut and paste. Cut and paste refers to the fact that that the solution to our problem depends on optimal solution to our subproblems. That is the cut and paste argument, which involves contradiction. Bottom up subtleties, that is fine. That is fine. That is enough. That is enough for optimal substructure. And now we can move on to overlapping problems. The second ingredient that an optimization problem must have for dynamic programming to apply is that the space of subproblems must be small. Yes, in the sense that a recursive algorithm for the problem involves the same subproblems over and over rather than always generating new subproblems. That makes sense. Typically, the total number of distinct subproblems is a polynomial size in input size is polynomial in input size. Typically, the total number of distinct subproblems is a polynomial in the input size. Okay, when when a recursive algorithm revisits the same problem repeatedly, we say that the optimization problem has overlapping subproblems because we are visiting the same subproblems again and again. And this dynamic programming would only work when the space of subproblems is small. The space of subproblems is small, and that would be small when we have subproblems overlapping with each other. Because if the subproblems are overlapping, there are fewer number of distinct subproblems. There it was like written here, distinct subproblems. And yeah, when this is true, when we are calling the same subproblem repeatedly again and again, we say that the problem has overlapping subproblems. In contrast, if problem for which we divide and conquer approach is suitable usually generates brand new problems. For merge sort, the problems do not overlap. For merge sort, the problems do not overlap every time new problem is created. And in those cases, we use divide and conquer approach. In contrast, problems which divide and conquer approach is suitable usually generates brand new problems. At each step of the recursion, dynamic programming algorithms typically take advantage of overlapping subproblems by solving each subproblem once and then storing the solution in a table or in hash table where it can be looked up when needed using constant time per lookup. So we are not wasting time for solving subproblems which we have already solved. We are doing some dynamic programming. Oh, this is why I ask. Yep. My bad. We are doing some dynamic programming study using this book, CLRS. This CLRS, Introduction to Algorithms, and we are currently reading about dynamic programming. Yesterday, okay, my laptop is going to die, but that is fine. Yesterday, we read about matrix chain multiplication, and the day before, we read about rod cutting, and now we are reading about elements of dynamic programming, which is very abstract, but this is going to help us a lot. Yep, that is a nice book. That is, I guess, the best book for algorithms. Now my laptop is not going to die. I'm happy. Yep, dynamic programming. Because if we can if it takes us time to go through all of these things, it is well worth it because we will understand what dynamic programming is and how it works. That is very worth it to go through this slowly and slowly. Slow is smooth, smooth is fast. That is a nice phrase. Dynamic programming algorithms typically take advantage of the fact that the subproblems are overlapping and we store the subproblems and we do not solve them again and again. We just, in constant time, look up the solutions that we have already solved. Section 14.1, the rod cutting example. We briefly examined how a recursive solution to a rod cutting makes exponentially many calls to find solutions of smaller subproblems. Yes, the answer was 2 power n. The dynamic programming solution reduces the running time from the exponential time of the recursive algorithm down to quadratic time, which is n square, which is n square is much better than 2 power n. N square is much preferred compared to 2 power n because this is going to take a lot of time. This is very slow. This is very fast. To illustrate the overlapping subproblems property in greater detail, let's revisit the matrix chain multiplication problem. Referring back to figure 14.5 at some point, observe that matrix chain order repeatedly looks up solutions to subproblems in lower rows when solving subproblems in higher rows. Yes, it was the case in figure 14.5. This one, when we are solving for this, we ask what is the solution of this, what is the solution for this, and what is the solution for these two. And yep, we are repeatedly asking for smaller things. And that is what we call overlapping subproblems. Observe matrix chain order repeatedly looks up the solutions to subproblems in low rows when solving subproblems in high rows. For example, it references entry M4 M34 four times during the computation of M when we are computing M24, M14 and M34. But this would also be okay. You took the lower limit and you higher limit. You fixed first the higher limit at 4 because we want 4 to be called, and then we varied the lower limit. Okay, and in these two parts, we did the same. Yeah, cool. If the algorithm were to recompute 3, 4 every time rather than just looking it up, the running time would increase dramatically. To see how, consider the inefficient recursive procedure, recursive matrix chain on the facing page. This one, which determines Mij, the minimum number of scalar multiplications needed to compute the matrix chain product from matrix I till J. This thing, the procedure is based directly on the recurrence 14.7, which we derived at while we were solving that question. Matrix chain multiplication shows the recurrence tree produced, figure 14.7. This one, yeah, this is the recurrence tree that will be produced, and here we are solving for 2 2 here, and we are again solving for 2 2 here. For 2 4 we have 2 4 here, and then yep, we have 2 4 here, we have 3 4 here. This is copied. We are solving for 4 4 again. We are solving for 2 2 again. We are solving for 3 3 here when we already solved it here, and for 1 1 for 2 2 again. For 3 4 we already solved it here, and since we are solving for 3 4 we are also solving for 3 3 and 4 4, and yeah, so all of these blue things are overlapping and we don't actually have to solve them. We could have just looked up in our table, which would have been better. Are you studying for college? I am new in programming. I would advise you to solve problems related to the chapters. This is how I learn and remember the concepts. Yes, that is also what I do. Like, I've solved a few dynamic programming questions, and when I've read this chapter, this whole chapter, I will go to CACS and I will be solving a few questions there on dynamic programming. I have solved these till now only, but I will also solve more when I've gone through these things. And also at the end of this section, there are some exercises which I will solve today in the stream. So that would be cool. And practicing is pretty cool. And thank you for the advice. And I'm not studying for college. This is far beyond college level. College is not going to teach you this. You cannot expect yourself to become better if you study just what is taught to you in college. And you are new in programming, I would suggest you can do CS50 if you want any suggestion, that is. If you don't, then you can just ignore me. You can do this course, Introduction to Computer Science by Harvard University, and this is completely free. All the lectures are free, and there are also a bunch of exercises. And this would be pretty cool for you since you are a beginner. That is what you can do. And yep. So they are saying that this algorithm is very shitty because this is solving the same problems again and again. P is the vector, the array which has the sizes of the matrices, and I and k are the limits. Plus this thing, and that is very shitty. That is very shitty. This is the direct implementation of this recursive algorithm. Noting that for I equals 1, 2, and n minus 1, yep, for the higher level, each term ti appears once as tk and once as tkn minus 1, and collecting the n minus 1 once in the summation together with the one out front, we can rewrite the recurrence as a separate. So noting that there is this one, and noting that for I equals 1 till I equals n minus 1, yeah, each term for I equals 1 and I equals n minus 1, each term appears once as tk and once as t n minus k. It appears once as, so 2 times, but what? Internally, when we are going through all of these. Okay, okay. I guess, okay. And collecting the n minus 1 once in the summation. This summation goes from 1 to n minus 1, and in each summation we are adding 1. So n minus 1 once plus this one which is outside, and the one out front which is this one, we get n plus n, and we can write our summation as this. Let's prove that Tn equals 2 power n. Okay, I do not get this part. How did we convert this thing into this? This thing makes sense. Plus I plus n minus 1 is n. But how did we convert this thing? Okay, this is not exactly equal. This is exactly equal, less than or equal to. K T K T K I is changing. So this is not exactly the same thing, but more like sort of the same thing. Each term Ti appears once as Tk and once as T n minus k. Yes, that makes sense. That makes sense. That shit. Yes, that makes sense. That makes a lot of sense. If we have a range from 1, 2, 3, 4, 5, and 6, and our I ranges from 1 till, let's say, 6, from 1 till 5, when I equals 1, we are calling the function for 1 and n, which is 6, 6 minus 1, 5. So first we called the function for 1 and 5 when this is the point where we are splitting the whole thing, right? For I, for k and n minus k. Let's call this k. When k is at 1, we are calling the function for 1 and 5. And when k equals 2, we are calling the function for 2 and 4. When 3 for 3 and 3, when 4, then for 2, and 5, then for 1. And in total, we are calling the function for every number twice, right? Twice. So instead of this recurrence form, we can write it as this 2 into ti, where I ranges from 1 to n minus 1, and that is cool. That makes sense. That makes sense. Yep, that makes a lot of sense. And yep, so this is correct. Now we are trying to prove that Tn equals omega n square. Let's try to prove it on ourselves by ourselves. So we are saying Tn is less than or greater than equal to 2 into summation n or I, we have I is ranging from 0 to n minus 1, and we are summing ti. We are summing ti plus n. If we write down, okay, so if we write down this thing like this, Tn depends on n minus 1 things, on t n minus 1, on t n minus 2, dot dot dot, t 0, and on all of them twice, since we have into 2 into this thing. And the cost for this layer is n. The cost for this layer is n. Hmm. So the first layer has one thing. The second layer has n different calls. And on average, you can say this thing will have n minus 2 function calls. This thing will have n minus 3 function calls in total, and dot 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 till this one will not have anything, and n minus at the end we will have one function call. So the total number of function calls here are going to be n minus 2 plus n minus 3 plus dot 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 till n till 1, which is a triangular number, and we can write it as t n minus 2 into n minus 1 divided by 2. The sum of this thing equals this thing. And where did we get this 2 from? 2 represents the second layer. So for, yep, but then for the third layer we would have a lot of things. Shit, this is going to be almost multiplied by 2 by n. So at the first layer we had n minus 1 calls. Then in the second layer, those n minus 1 calls in total had this many function calls, which we can say is like n minus 2 divided by 2. If we have n minus 1 functions t's at a layer, it is going to call n minus 2 divided by 2 function calls. That is almost correct, I think. And then the next one would have n minus, everything depends on what I write next. N minus 3 divided by 2. N minus 3 divided by 2. I think that is correct. And this will keep on going. And that will be the total number of function calls. And this will keep on going till 1. This is like sort of like a GP. Okay, let's just look at what they are doing there. That would be better. Let's prove that Tn equals worst case, average case, omega 2 power n using the substitution method. Specifically, we will show that Tn is greater than equal to 2 power n minus 1 for all n greater than or equal to 1. For the base case n equals 1. Okay, the summation is empty For the base case n equals 1, the summation is empty. So we get 2 power 0. Okay. Inductively, shit, we can use induction. We can use induction. We can use induction. For base case, okay, since this, okay, fuck shit. We have our formula Tn equals to summation Ti, where I ranges from 0 till n minus 1 plus n. And our formula says Tn equals 2 power n minus 1. Yeah, greater than equal to 2 power n minus 1. And this thing is also greater than equal to this thing. And the formula that we want to prove is this. So for base case, when n equals 1, we have from our inductive case, this thing is 1. And if you apply our formula, like here, we will get 2 power 0, which is also 1. So that is correct. Our base case is correct. And my bad, my phone is ringing. Wait a minute, just a minute. I have to see. Okay, it is fine. I completely fine. It's a friend of mine. Yep, face cam is working. That is cool. And back to the question. So using induction, we can prove this. We can actually prove this. So for our base case, when n equals 1, we have our base case is working. U1 equals 1, which is also equals 2 power 0. So our base case is absolutely amazing. And we have from our recursion 2 power summation I goes from 0 to n minus 1 till t I, we don't need this bracket, what the heck. Yes, ti plus n. And if we plug this formula 2 power n minus 1 in here, let's see what we get. T n equals 2 into summation I ranges from 0 till n minus 1, and ti would be 2 power, by induction, ti would be 2 power I minus 1 plus n. And I think we can expand this series. Of course, we can expand this series, and we are multiplying the whole thing by 2. So we can write this as summation I goes from 0 till n minus 1, 2 power I. Since we multiplied every term by 2, so the power increased by 1. So I minus 1 plus 1 is just I, and plus n. And this thing, we can write this as 2 power n minus 1. This series is equal to this sum, and then we add n to this thing, and we add the sign from the beginning. And what do we have here? We have 2 power n minus 1 plus n. Is that what they have there? 2 power n minus 2 plus n. Why do I have minus? 2 power n minus 2 plus n, and yeah, I mean, like, whatever. Yeah, and we can write this as 2 power n minus 1. we subtracted n, we removed -1, and we divided the remainder by 2. So whatever on the right side was, it is still guaranteed to be greater than 2 power n minus 1. Therefore, this thing is proved by induction. By induction, Tn not equal to, but it is greater than equal to n power this, n power 2 power n minus 1 by induction. That is cool. And also, yep, that is cool. And which completes the proof. Thus, the total amount of work performed by the call recursive matrix chain P1 to n is at least exponential in n. Yep, it is at least. It might be greater because we have greater than equal to sign. So it is at least this thing. Compare this to top-down recursive algorithm without memorization. And this is the time complexity for a algorithm, for a dynamic programming algorithm without any memorization, and that is very bad. The latter is more efficient because it takes advantage of the overlapping subproblems property. Matrix chain multiplication has only n square distinct subproblems. Distinct is the main word there, because we are solving all subproblems and the total number of subproblems is n square, which is a lot better than 2 power n. The recursive algorithm, on the other hand, must solve each subproblem every time it appears. It will have to resolve each subproblem every time it appears, and that is bad because it does not take advantage of the fact that we can use memorization. Must solve each subproblem every time it reappears. Yep, reappears, not appears, reappears. If it is only appearing for the first time, then it is cool. We would have to solve it anyway. But if it is reappearing, then do not solve it again. In the recursion tree, whenever a recursion tree for the natural recursive solution to a problem contains the same subproblems repeatedly, and the total number of distinct subproblems is small. The total number of distinct subproblems is small. Dynamic programming can improve efficiency and sometimes dramatically. And that is true. That is like really, really true. Reconstructing an optimal solution, that would be the next step. But from this, we can conclude from this whole subproblem part, overlapping subproblem part, we can conclude that depending on the number of distinct subproblems that we have, dynamic programming can drastically improve our running time. And that is cool. Reconstructing an optimal solution. As a practical matter, you will often want to store in a separate table which choices you made in each subproblem so that you don't have to reconstruct this information from the table of costs. Yes, because solving a dynamic programming question involves making a bunch of choices at each level and finding out which choice is the best. So we could store the choice that is the best in some separate data structure, and then when we are constructing the solution, the solution which involves finding out which choices were made to get to the best optimal solution. If we already have a data structure which contains all the choices that we made, then we can just access that and construct our solution. For matrix chain multiplication, the table Sij, this is two-dimensional, saves a significant amount of work when we need to reconstruct an optimal solution. Suppose that the matrix chain order produced on page 378 did not maintain the Sij table, so that if we didn't store our extra information in this data structure where we are storing the choice that we are making, Is it audible? It's my phone is audible and my camera is also working, but that is fine. That is fine. My camera is working. And it should be in do not disturb mode, but it is apparently not. And let me not see. That is fine. So what we need is we have to have a data structure which is storing the choices that we are making at each level. Let me actually see who is calling. Wait a minute. Now it's fine. Now it is completely fine. Yep. Shit, the camera is like straight up into my face. That is very weird. That is very weird. That is very bad. Looks very bad. Shit. Anyways, memorization. Yeah. So whenever since dynamic programming involves making a bunch of choices and finding out which choice is the best, we can have a separate data structure which stores the choices which we made to get to the optimal solution. And going through that data structure, we could construct the solution which led us to the optimal solution which we got. The procedure chooses from among, yeah, that is fine. The procedure chooses from among j minus I possibilities. Yep. At every j to I range, we have j minus I choices. And if we have a separate data structure, to say it again, which has the choices which were made for particular I and for particular j's, if we have that, then it is cool. We can just look it up, what were the choices that were made, which led to us finding that optimal solution. We can just construct the whole thing, which we actually did yesterday. Steamux is not running, that is cool. And if you go to the matrix chain multiplication, this is what we wrote yesterday, and this part cuts. This stores the choices which we made, and everything else is just the code. And we go G++, and if we run the matrix chain multiplication, or first we have to compile it. It is compiling, and we will have to give it some input as to what the matrix is like. We can use this one, 30. Let's use a smaller one. That is too big. No, that is fine. We can use 30, 35, 15, 5, 10, 20, 25. How many numbers are those? Right. We have 6 matrices, so the size would be 7. 7 is the size, and in 7 we have 30, 35, 15, 5, 10, 20, 25. 30, 35. I am stupid. 30, 35, 15, 10, 20, 25. But that is just 6 numbers. 30, 35, 15, 5. 5, 10, 20, 25. And the answer is 15, 1 to 5, which is the correct answer. 15, 1 to 5. And we also have the solution, which led us to that thing. This is the solution. And this is the optimal value, which was given by this solution. And here we are getting 2 solutions because the first one uses iteration and the second one uses recursion. So we implemented both the solutions using recursion and iteration both. So that is the reconstruction part. Now the memoization part. As you saw, memoization is used with recursion, As we saw for rod cutting problem, there is an alternative approach to dynamic programming that often offers the efficiency of bottom-up dynamic programming approach while maintaining a top-down strategy. The idea is memorization, the natural but inefficient recursive algorithm. Yep. Yeah, memorization is natural, it is recursive, but it is not very efficient. As in the bottom-up approach, you maintain a table with subproblem solutions, but the control structure for filling in the table is more like a recursive algorithm. Yeah, yep, that is true. In bottom-up approach, we are saying we are like very specific about how we are filling our table, but in recursion, we are not very specific. We are just memoizing using a data structure to solve solutions for subproblems which we have solved, and then later we just look it up in the memoized data structure. A memoized recursive algorithm maintains an entry table in a table maintains an entry in a table for the solution to each subproblem which have been solved. If it hasn't been solved, then we solve that subproblem and we update the table. Each table entry initially contains a special value to indicate that the entry has yet to be filled in. Yep, yep, initially everything is not filled in. When the subproblem is first encountered, as the recursive algorithm unfolds, its solution is computed and then stored in the table. Yes. And then whenever we want the solution to that particular subproblem, we just look it up in the table. Each subsequent encounter of this subproblem simply looks up the value stored in the table and returns it, so that we do not have to calculate it again. We have so-called memoized the solution. The procedure memoized matrix chain is this one, memoized matrix chain. Here we have this table and we are iterating from I1 to N and lookup chain, lookup chain, lookup chain. Here in this part, we are setting up all the values in this two-dimensional matrix to be equal to infinity, which is equivalent to initializing it, which is equivalent to initializing the answer, so that we know that this entry is not yet filled in. And yeah, it is not yet filled in. And then we go through all the subproblems and we fill it up whenever we have solved a subproblem. But, but, yeah, we just fill it up and we are referencing things and yeah, that is cool. That is cool. If we already have solved it, if mij is less than infinity, if we have solved it, then return the thing. That is cool. And I'll be right back. I have to go to the washroom, and while the camera is like right in my face, that is right in my face. I'll be right back in a minute. Wait a minute. And I'm back. And I actually have to fix this camera. Wait, now it is fine. Seems like it is fine. No, it is still in my face, like right up in my face. It is fine. It is fine. The camera is fine. So this one uses memorization, and which is much better than solving all the subproblems again and again. And memorization, if we were to write something about memorization itself as an independent topic, that is far too small. Memorization. What are the things? So, memorization, we use this with recursion. We use this with recursion, and this helps us in avoids resolving sub problems. That is kind of it about memorization. We use memorization with recursion, and this avoids solving the same subproblems again and again. That is kind of it about memorization. Yeah, in top-down approach, we don't even have to write top-down. Let's just write top-down approach. Recursion uses top-down approach, and if we use memorization with recursion, we are much better. And instead of, yeah, like this, recursion at the top, recursion uses top-down approach and memorization helps in avoiding subproblems, avoiding solving the same subproblems again and again, which is cool. So that is the thing. Recursion uses top-down approach, and when armed with memorization, we do not have to solve same subproblems again and again. So we are only solving distinct subproblems. Hello, I am from India. Yep. And shit, I guess you wanted me to be more specific than that. I don't know. There is a state. I'm from northern India. Yeah, that is a nice answer. That answer feels like I'm educated. I'm from northern India. Yep. And I again lost it. Where were we? We were at, okay, and this is the next part, longest common subsequence. This is what we will be reading tomorrow, and it is going to be very fun because we will be writing. Most of the time we will be writing code. Today the thing was mostly abstract. Yeah, we are already here around the end. Today most, keep going, bro. Yep, thank you. I will not stop. No one will stop me. I will keep going, and I will reach a rating of 2000. And when I do reach a rating of 2000, you will be able to see that you also can reach a rating of 2000, because I don't think I'm more smarter than you. And if I can do that, you can also do it. And it would be pretty cool. Here, the memoized matrix chain procedure, like bottom up matrix chain order, matrix chain order procedure on page 378, whatever that is, maintains a table. Yeah, we like, yeah, we maintain a table, lookup table, this one, because if you already have the answer, we just return it instead of calculating it again. Maintains a table M of computed values, Mij, the minimum number of scalar multiplications needed to compute the matrix Aij beginning from I till j. Each table entry initially contains the value infinity to indicate that it has not yet been solved. Upon calling lookup chain first, we see if it has been solved. Then procedure simply returns the previously computed cost on line 2. Otherwise, if it hasn't been solved, then we solve it the same way that we were solving in recursive chain multiplication, and then we store the answer in Mij, and then we return Mij. So that is cool. Like the bottom up procedure matrix chain order, the memoized procedure memoized matrix chain runs in log 3 n cube time. So the time complexity for both bottom up procedure, which was this one matrix chain, and this top down procedure memoized matrix chain, is n cube, but Bottom up is a bit faster because it has lower constant factor, because we are just running a loop compared to memoized matrix chain, in which we are using memoization and recursion. There we are calling a function, and calling a function has a higher overhead compared to bottom up, where we are just directly referencing values from a vector. To begin with, line 4, memoized matrix chain executes n square times, which dominates the running time outside of the call. And then matrix chain and line 5, this one internally we are iterating. I mean the journey, not how did you start? Journey. Shit, that how did you start? Shit, that is something which was said in the last episode of Mr. Robot. Not the last episode, but yeah, in season first of Mr. Robot. But yeah, how did I start? Well, there is a philosophy, I think, that like nihilism, most of the things don't seem meaningful to me. Most of the things seem like meaningless. So I'm training myself to pick any arbitrary thing and call that thing very meaningful, and giving out all of my energy to get better at that thing and pursue that thing at the best of my ability, and in the process also improve myself, and then come out the other side as a better human being, improved human being who has grown up. And that I'm doing for any arbitrary thing, which at this point is competitive programming. So if I get the ability, if I can develop this ability where I just pick any arbitrary thing and I can get better at it, I think I will become very strong, because I can just point to any one thing and say that I'm becoming better at this thing, and I will become better at this thing because I'm training for that in some sense. Even though that thing might have no real purpose to me, but I can pretend that it has some purpose. And yeah, that is kind of like the philosophy. This is very similar to what this has like influence from David Goggins and Jordan Peterson. And yeah, that is what I'm working on, the journey. Because till this point, I've been very mindless. I haven't paid attention to a lot of things. And yeah, I feel like I'm like, compared to an average human being, I feel like literally feel like I'm stupider compared to an average human being. So I have to work harder. And I decided that I would work harder instead of saying that I'm stupid. So I'm working hard. And yep, lookup chain in line 5. So that is like the time complexity. The time complexity of top-down approach and bottom-up approach is both n cube is n cube in both the cases. And yeah, lookup chain has two things. First, if we already have the answer, then we return. If we do not have the answer, then we execute. So there are n square calls of the first type. N square calls for the first type to fill every entry. And all of those n square calls internally run n times, or something similar to n times. So n cube in total. There are n square calls for the first time to fill up every single entry. It makes O of n of them. Yep. Whenever we give a call of lookup n chain makes recursive calls, it makes O of n of them in worst case, when I equals 1 and j equals n. Therefore, there are n cube calls of the second type. in all. Each case of the second type takes constant time, and each call of the first type takes n time plus the time spent in the recursive call, which is a higher overhead than what we would get in a bottom up approach. The total time therefore is n cube. Yes, that I can agree with. Memorization thus turns an exponential time algorithm into a quadratic time algorithm. Even though this is not very optimal, but it is much better than 2 power n. We have seen how to solve the matrix chain multiplication problem by either a top-down memoized dynamic programming algorithm or a bottom-up dynamic programming algorithm in n cube time with tabulation. In bottom-up, we use tabulation. Both the bottom-up and memoized methods take advantage of the overlapping subproblems property so that we are not solving the same subproblems again and again, and we are reducing the exponential time into quadratic time. There are only n square distinct subproblems, and each distinct subproblem at worst runs n times. Check to your channel, please be being consistent as you are, and you will reach 2000 and reach your goal. Best regards. Thank you. Thank you. I will keep going, and thank you for this thing. Thank you for your kind words. I will reach a rating of 2000. Don't worry. And this is something Cameron Haynes' son, Truett Haynes, said, that you do not rise up to the occasion, you fall down to your practice. So practice hard. I'm practicing hard. Without memorization, the natural recursive algorithm runs in exponential time. Uh-huh. Yep. Yep. It is 2 power n exponential. Bad. Very bad. Since solved subproblems are repeatedly solved. Yes, it's bad. In general practice, if all subproblems must be solved at least once, all the subproblems must be solved at least once, a bottom-up dynamic approach usually outperforms the corresponding top-down memoized algorithm by a constant factor because the bottom-up algorithm has no overhead. Yep, overhead for recursion and less overhead for maintaining the table. Yes, because we are directly accessing entries in the table and we are not doing a function call to get some answer. Moreover, for some problems, you can exploit the regular pattern of table access and we can reduce the space complexity, right? Yep, we can reduce the space requirements even further. On the other hand, in certain situations, some of the subproblems in the subproblem space might not need to be solved at all. In that case, recursion is better. In that case, the memoized solution has the advantage of solving only those subproblems that are definitely required. Yeah, so there is a balance that we have to see. Do you believe some people are better? I mean, who's 2000 plus rating or 16 are different from us? I think they have they are different in the way that their mind works. They do not look at difficult questions and think, oh shit. I mean, they might think, oh shit, but they do not think that they are not good enough, that they won't be able to solve the question. Like, they do not think that no matter how hard they practice or give how much time they give to this question or some particular topic, they won't be able to understand it. Their, I think, mindset is if they work hard or like if they want to and spend time on a particular concept, they will be able to understand it. And the fact that they do not understand it right now and are unable to solve some hard question is because they have not spent enough time on that question or on that concept. And that is the time mindset that I am trying to develop by going through, by giving time to things, and going through things slowly and graciously. And shit, no data, what the heck? Stream is running. Stream is running. Okay, that is fine. Yeah, so that is what I believe. That is what I believe. And the mindset is the main difference. And the mindset that we have, generally speaking, is that let me learn about this topic so that I can get good marks in my exams. But that is not the right thing because it is very limiting. It is a very limiting mindset. And yeah, mindset is the main difference, I would say. Now this thing, which is a more efficient way to determine the optimal number of multiplications. Yes, questions. Okay, yes. Let me come back into the present moment. Which is a more efficient way to determine the optimal number of multiplications in a matrix chain? Okay, and what is uh, optimal number of scalar multiplications in a matrix chain multiplication problem? Enumerating all the ways of parenthesizing the product and computing the number of multiplications for each, or using recursive matrix chain. Justify your answer. Okay, I would say because in this recursive matrix chain, we are not using memoization. So the sample space through which this one, recursive matrix chain multiplication, and this inefficient one in which we are going through all possible ways of parenthesizing the product, the sample space for both is same, and it is Catalan numbers, the nth Catalan number. If we have n matrices, that would be the sample. The sample space is same, but this one enumerating through all the ways of parenthesizing is faster because it has lesser overhead over this recursive approach, right? That makes sense. That makes sense. And in this case, recursive is slower due to the same reason that it is generally slower compared to a bottom-up approach. Here, the sample space is same, but the overhead in recursion is higher, which increases time. So justify my answer. That is my justification. And are there solutions to this thing? I can go to ChatGPT and ask if my answer is correct. I don't think there are answers. So let's go. ChatGPT, this is the question, and my answer is that the yes, I have to clarify. This doesn't use memoization. My answer is that going through all the ways of parenthesizing the music is faster. And the justification is that the sample space which we have to solve in both the algorithms is about the same, but the overhead in the recursive algo is very high compared to the overhead in the other algorithm. And there, for the recursive algo is slower due to high overhead. You're close. Shit. My conclusion is flipped. Let's go step by step. Okay. The two approaches, enumerating all ways to parent. Yeah. I said Catalan numbers. I did say Catalan numbers. So brute force enumeration is super exponential. Super exponential. Recursive matrix without memorization. This algorithm is recursively tries every possible split k between I and k at each subproblem. Many subproblems are recomputed many number of times. The complexity is still exponential, roughly 2 power n, but not as bad as enumerating all parentheses. Why? So my assumption that the sample space is same is not correct. Comparing the two, enumeration approach explores every single parenthesization explicitly, Catalan number growth, which is about n power 4. And recursive approach without memorization explores fewer cases because it just tries every split, not every parenthesization, but it's smaller. Okay, therefore, correct justification. The key idea, enumeration explicitly considers all parenthesization, and recursive indirectly covers the same search space but in more compact way. How can you search the same search space, which is supposedly 4 power n, but in a more compact manner? So enumeration is worse because the sample space is higher. But how? So how recursion searching through the whole sample space without with l- going through lower number of possibilities. How is that happening? Yep, that is kind of strange. Excellent question. Okay, if you explicitly enumerate parenthesizations, you are saying let's generate every distinct parenthesization tree, binary search tree, BTS. The number of such trees is the Catalan number. That I agree with. Each tree corresponds to one way of multiplying the matrices. That's already astronomically large. Okay. What does recursion do? The recursive matrix chain function does not first generate all parenthesization and then evaluate them. Instead, it computes only costs on the fly using recursion. At each level, it splits into two, recursively computes the cost for left and right subchains, then combines them. So instead of explicitly listing parenthesization recursively, implicitly considers them by splitting the problem in every possible way. Okay. 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 Because enumeration distinguishes between different parenthesization trees, even if they represent the same subproblem. Recursion, on the other hand, defines subproblem by interval ij. So what is at play here is divide and conquer. What conquer? That is CONQUER. Divide and conquer. We are using divide and conquer, and that is somehow reducing the number of problems that we have to solve. The same thing we use in merge sort. We are using the same thing here, divide and conquer. And here recursion is slow compared to memorization, because when we divide, the problems that we get are similar. We are not using memorization, so we are solving the same subproblems again and again, but this is still better than going through them manually, because this is still better than going through them manually, because we have divided the problems. Okay, I will have to read up more on that, but that is cool. That is cool. Divide. Dividing the problem gives us smaller number of subproblems. That is cool. That is cool. And the thing that we are lacking is red. The thing that we are lacking is overlapping subproblem. Yep, this is what we don't have. And what we do have is smaller search space. That is cool. This is what we don't have. And that is why that is why recursion is better than going enumerating all the ways to parenthesize. Okay, that was a nice question. That was a actually nice question, and we are somehow at the start of the book. This is chapter number 15, which is greedy algorithms. We are not doing that yet. Right now, we are solving questions. For 14.3. This is 14.3. Yeah. So we did that one. I clicked there again and we messed up. 15, we are again at greedy algorithm. Yep. Now we are back. Now this thing. Draw the recursion tree for merge sort. Okay, I can do that. Procedure from section this on array of 16 elements. Explain why memorization fails to speed up a good divide and conquer algorithm such as merge sort, because the problems are not overlapping. Let's say we have a vector, an array of 16 elements, which is white, from 1 till index 16, and then we divide this and we get two smaller arrays of sizes 1 to 8 and 9 to 16. Those are the new arrays that we get, and then we divide these further into smaller arrays of size 1 to 4, and then from 5 to 8, and here 9 to 12. Yes, 9 to 12 and 13 to 16. And what we get is something like this. Paste, paste, and then paste. And then we further divide them with size 1 to 2, and then 3 to 4, and then 5 to 6, and then 7 to 8, and then 9 to 10, and then 11 to 12, and then 13 to 14, and then 15 to 16. And here we can see at this point we have hit our base cases. These are our base cases. But the problem is why memorization here fails is these base cases are not overlapping. These are independent. I mean, these base cases are independent, but to solve a particular subproblem and then to solve those subproblems, the subproblems on which the solution for this subproblem depends on, these subproblems are unique to this particular subproblem, and therefore these subproblems do not overlap. For each particular subproblem, the subproblems on which it depends on are unique for that problem. And therefore, memorization is not pretty good here. So therefore, recursion, we do not use memorization with merge sort. Consider the antithetical variant of the matrix chain multiplication problem, where the goal is to parenthesize the sequence matrices so as to maximize rather than minimize the number of scalar multiplications. Does this problem exhibit optimal substructure? Yes, this does exhibit optimal substructure, which we can actually write for iteration copy paste, and we will call this maths. This takes in a vector and initially we are not doing this step now, and we will update whenever new is greater than what we have. Let's go down here when we are calling the iteration function, and let's call the max variant. Okay, it does compile, that is cool. And we have 7 things, which are 30, 35, 15, 5, 10, 20, 25. Okay, I messed up at some point. Minimum number of scalar multiplications, and here instead of recursion, let me call the iteration variant. It only takes in V, and here let's say maximum. G++ does compile, and it is waiting for the input 7, 20, 25, 15, 5, 10, 20, 25. And okay, the minimum part is messing up, maybe because I'm not giving the right input, because this is the same as I got before. Okay, what was the original input to the question? These 30, 35, 15, 5, 10, 20, 25. There are 7 numbers: 30, 35, 15, 5, 10, 20, 25. 30, 35, 15, 5, 10. 2025. 30, 35, 15, 5, 10, 20, 25. And yes, so I was inputting the wrong number. But yeah, the things do not overlap, so we will get the right answer, and the substructure is optimal. So the answer for that question is yes, the substructure is optimal because the subproblems are wait, yes, the subproblems are independent. The subproblems are independent. Yes, the subproblems are independent. Therefore, the substructure is optimal for this thing. The answer is yep. The substructure is the optimal substructure. The substructure is optimal. And let's just confirm, just in case. Here, my answer is that the problem exhibits optimal substructure since the subproblems are independent. To try shit. In the minimization case, the maximization version also exhibits optimal substructure. Okay, that is cool. But independent versus optimal. Careful, independence of subproblems is not enough to guarantee optimal substructure. The key property is the optimal global solution. Yeah, I mean two things. Yeah, it depends on two things. First of all, the problems are independent, and second of all, the local optimal results in the overall global optimal. Those are the two things that you have to keep in mind. Right? The camera is right in my face, into my face. Okay, so that is cool. That is cool. We did that. And now the second last question. As is stated in dynamic programming, you first solve the subproblems and then choose which of them to use in an optimal solution to the problem. Professor Capulet claims that female, that she does not always need to solve all subproblems in order to find an optimal solution. She suggests that she can find an optimal solution to the matrix chain multiplication problem by choosing the matrix AK at which to split the product by selecting K to minimize the quantity before solving the subproblems. Find an instance of matrix chain multiplication problem for which this greedy approach yields a suboptimal solution. What is? She suggests that she can find an optimal solution to the matrix chain multiplication problem by always choosing the matrix AK at which to split the product. No, she cannot know this beforehand. Yeah, I mean, this like obviously does not work. The greedy algorithm does not work because we have n-1 choices and she cannot know beforehand where to split. And even if she knows where to split, yeah, if she is just saying, pointing fingers and saying split the matrix chain at this point, it is not going to be optimal because she does not know which is the place where to split it. And what is the parameter on which she is choosing where to split? She suggests that she can find an optimal solution to the matrix multiplication problem by always choosing the matrix AK at which to split before solving the subproblems. How would she choose find an instance of matrix multiplication for this? Okay, she is not stating how she is choosing the AK product. Then if we suppose that it is random, then it is not guaranteed to work. For the last question, suppose that the rod cutting problem of section 14.1 also had a limit Li on the number of pieces of length I allowed to be produced for I equals 1 to n. Show that the optimal substructure property described in section no longer holds. Yeah, so because now the subproblems are not independent, right? They are not independent anymore. Yeah. Because if you choose a piece of length I on one side a particular number of times, then that affects that has an effect on how many pieces of the same size you can choose on the right side. So the optimal substructure is gone now. It is in shackles. It is like broken. So and I think that is enough for that part. And tomorrow, longest common subsequence, which is one of the hardest dynamic programming questions. And it is going to be cool. For tomorrow, it's going to be cool. And for today, this would be the end of today's stream. And thank you for being here. Bye. It's been quite long actually. And thank you for being here. Bye again.